right, can you can Zoom people, can you guys hear me now? Oh, okay, good. Okay. Right. So I was saying, so this week is a short week. So we have just the midterm exam on Wednesday, and then just one lecture today. Okay. So we're going to start something new today. Of course, this is not going to be on the midterm exam. Although I did notice today that there's a couple conceptual problems on homework 5 regarding this. You won't be responsible for that for the midterm exam, but if you were curious about how to do, I think, the last two conceptual questions on problem 1, then we'll cover that today. Okay. But the reason I'm covering this topic just because we're pretty much wrapping up the semester at this point. Because next week, of course, is Thanksgiving. We don't have any lectures next week. When we come back from Thanksgiving, we'll have one more week of lecture, and then that final week, week 16, is going to be just all final presentations. And so we're pretty much wrapping up. So this is going to be the last kind of major topic that we'll cover, and we'll probably do this for the last 3 lectures that we have. Okay. Okay. And so with that said, I know homework 5 is due tonight, and so you definitely want to make sure you finish that. Because the midterm exam is Wednesday, I'm going to post the solutions for homework 5 pretty much right before I go to sleep, and so you'll have that to study for the exam. Okay. So remember, for the midterm exam, you can bring in your writing utensil. You can bring a calculator. You can bring a cheat sheet, and so that's 1 8.5 by 11 sheet of notes. Same as the midterm exam, and so same as the first midterm exam, and so you can do the same for this one as well. Okay. So I have a couple office hours, or I have just one scheduled office hours before then. So I have office hours tomorrow morning from 9 to 10. But I know there's at least a couple of people coming by my office after lecture today. One for this class and a couple for a couple of my other courses. And so if you had some questions right after the class today, I'm going back up to my office, and you can join for that. Okay. But besides that, I have just office hours tomorrow morning. And if you want to meet, if you have any last minute questions, just email me. We can try to set up a time kind of outside of that. Okay. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and start. So the topic today is muscle force optimization. Okay. So muscle force optimization, you can think of it as kind of the last step in terms of our dynamic analysis, right? So we've gone over kind of 3. This is the third of the 3 kind of topics that kind of completes this analysis, right? Because ultimately, what we want from our dynamics analysis is basically the same thing as what we get from static analysis, right? Okay. And what that is basically computations or measurements of the muscle forces and joint reaction forces as a function of time as the human body undergoes some motion. Okay. Okay. Because that's ultimately what we had in our static case, right? And so in statics, we drew a free body diagram, and from the free body diagram, we were able to find the muscle forces and joint reaction forces. Okay. In dynamics, of course, it's a lot more complicated just because we have motion. First of all, even just measuring the kinematics is non-trivial, right? Okay. And so in order to obtain what we want, we have to kind of go through 3 stages of analysis, right? Okay, so the first step is human motion kinematics. So that was the motion capture stuff that we went over a few weeks ago. Two, we have inverse dynamics, and so inverse dynamics is kind of what we just finished up, right? And so from inverse dynamics, what we did was we took the information, we took the data from human motion kinematics and converted those into kind of net forces, net moments at the joints. Okay, so that's part of the puzzle, right? But we're not quite at the point where we're computing muscle forces, right? Because what we kind of obtained at the end of inverse dynamics was, in order to produce this motion, you need to have a certain moment or a certain force at the joints. Okay, and so the last step of this process is to kind of take the results of inverse dynamics and then actually use those to compute individual muscle forces. Okay, and that's what we're going to do this week. And so this is called muscle force optimization. Okay. Mathematically speaking, this last step here is probably the most complicated, and very, very likely that something that you have no exposure to before at all, unless you're also just happen to be in my 454 class on Tuesdays and Thursdays. Then you have been exposed to it for the entire semester. But that's not a required class, so most people aren't aware of this. Okay. So why is it so complicated? Right. So why am I kind of hyping up this last step here as being so hard? Well, the difficulty comes from actually something that's a very nice feature of the human body, which is also just generally a good feature for just engineering systems in general, and that's redundancy. Okay. Okay. And so if you're unfamiliar with the term, or if you're unfamiliar with the concept of redundancy, basically the idea is that when you want a certain task to be done, or you have a certain expectation for a certain output that your system needs to deliver, right? Whether that be a certain motion or maybe a certain product that you're developing, right? You don't want it to rely all on just one step or just all on one feature, right? You kind of want to spread that out across multiple different systems or multiple different agents, so that if one goes down, or if one gets hurt, or if one for some reason or another can't produce the output, you don't have to kind of totally shut down. You can kind of rely on the other parts of the system. Okay. And in the case of biomechanics, what redundancy basically means is that we have multiple muscles in the human body that can produce the same or similar motions. Okay. So redundancy in general is a good idea to design with. And so if you're designing, let's say the air conditioning system in a building, right? You don't want it all to rely on just one machine, right? You want to have multiple different machines. So if one goes down, people in here just aren't baking in the summertime, right? And so same thing with the human body, right? And so if a certain muscle gets injured, or if a certain muscle is compromised in any way, it's not going to, it's probably going to hurt, but you'll still be able to do certain functions because of different muscle groups, or different muscles can do that same thing. Okay. But mathematically, this makes things really complicated, because when you form equations for redundant systems, what you end up with is usually more more unknowns than you have equations. Okay. And so your approach to solving these problems, at least from a mathematical point of view, has to kind of change. And so we can't usually rely on our typical algebraic tools to solve these equations. We have to kind of take a different approach, and hence that approach is called optimization. Okay. All right, so we've seen this a little bit already. So we talked about this a bit in statics, right? And so the one example that I kind of come back to is let's say that you want to flex your elbow, right? Okay, there are three main muscle groups that can help with this, right? And so if we draw kind of our arm here, okay, we have three muscle groups, and so we have the biceps brachii muscle. I'll just kind of draw lines for them, right? So this one here is biceps brachii. Okay. We also have the brachialis muscle. So the brachialis muscle maybe looks something like this. Okay. And then we have the forearm muscle. So this is the brachioradialis. Okay. And so because of the way all these muscles attach, all of them can contribute to elbow flexion, right? And so you can see that both of them have attachment points on the upper arm and the lower arm. And so if any of these muscles were to create tension and shorten, then they would all flex the elbow. Okay. And so the question then becomes, how do we split the work, right? So, do we just rely on one muscle? Do we spread it out across the different ones, right? But each muscle also has their own properties as well, right? So they all have their own lengths, their own cross-sectional areas, and so the maximum amount of force that each muscle can produce is different, right? And so it kind of very quickly becomes kind of a complicated problem in terms of how to compute these. But computing these is important, because if we want to kind of really understand kind of how the body produces motion, we want to be able to compute each of these individual muscle forces. Okay. Okay. Any questions on this so far? Okay. All right. So how do we choose that, right? And so there must be some criteria that the body uses in order to choose which muscle groups get activated, right, and how much we activate them. Okay. So I've kind of already hinted at how we're going to solve it, right? Mathematically, we're going to use optimization, right? But the human body, it doesn't really have knowledge of 70 years of applied mathematics, right? It has its own way of kind of deciding kind of which muscles to use and how much to use them, right? And so that kind of begs the question of how do we actually do this, right? Well, I'm going to give you the most political answer that you can give, is that it depends. Right? Right. That seems to be kind of what everyone's saying nowadays. That depends, but it really does. But in this case, it really does depend on the situation, right? Because when your body undergoes motion, when your body tries to accomplish a task, usually the goals are different each time, right? So I'm going to give you a couple of examples. And then from these examples, you can hopefully see that, the goal is going to be different from each one. Okay. And so first, let's start with kind of a very kind of relaxed thing. So let's say that you're just walking from, class just ended and you're walking from the classroom to your car. Okay. You're not really in a hurry, and you're just kind of taking it at an easy pace. Okay. But you have to activate your muscles in order to get there, right? You have to kind of move your body from point A to point B, right? And so in this situation, the criteria that your body would use is maybe something like energy conservation, right? And so you want to get from point A to point B, and you want to do it in the most energy efficient way possible, so that you can kind of save your energy, once you get home to, I don't know, do homework or party, whatever, right? Okay. Okay. So another example, so let's say that you're walking to your car and then you turn the corner and you see a gigantic tornado of sharks. So, and you're being chased by it for whatever reason, right? Okay. So that's a very different situation, right? So you're not, and so in that situation, you're not really looking to conserve energy. You're kind of looking to conserve your life, right? And so in that case, probably probably what you're going to do is you're probably going to run like hell, right? And so in this case, one way that we can sum this up is that we're looking for optimized performance, right? Okay. We'll do one more example. Right? And so let's say another example that you are calling your body to do is that maybe you work as a concert violinist, right? And so you're kind of responsible for playing the violin. The violin is a very delicate instrument. It takes a lot of years of practice and a lot of talent to really play really well. And so in this case, it's you're really kind of looking for more stability and control, right? Right. So you want to control your muscles as precisely as possible, so that you can hit the notes, you can play the instrument, kind of exactly as you need to. Okay. Okay. And so and there literally probably millions of other types of scenarios that you come up with, right? But I bring these three examples up just because these kind of show usually when your body wants to do something, there's different objectives depending on the situation. Okay, and then depending on those objectives, depending on what you need to accomplish, that's going to affect how much muscle force you're going to use, how you're going to split the work between the muscles. Okay, so all this kind of factors into that. Okay, all right. And so, like I mentioned, right, the mathematical tool that we're going to use to solve these problems is called optimization. Okay? So basically, the idea with optimization is that it's you can almost think of it as kind of a different framework or a different way to solve kind of mathematical engineering problems. Okay. It's very broad, right? And just like I kind of mentioned, we have I'm teaching an entire class dedicated to optimization. Okay. But for our intents and purposes, what you can kind of think of it as optimization is a way to solve for the solution to situations when you have more unknowns than equations. That's kind of a very, very broad way to kind of put it. Okay. Okay. And the nice thing about optimization is that there's ways that you can kind of tweak it or modify it to give you different solutions under different situations. Okay. I think that's probably the most broad definition I can give it at this time. Okay, optimization means a lot more. So for those of you in 454, we've been talking a lot more. But that's kind of what the gist is. Okay. All right. Any questions? Any questions on this so far? Okay. All right. So optimization isn't just limited to biomechanics, and so in fact, optimization is used in lots of different areas of engineering. Okay, and a lot of times, you'll use optimization to solve kind of very difficult engineering design problems. Okay, and so some examples could be, maybe you're designing the optimal dimensions for an airplane wing, right? And so that's a situation which has tons of variables and tons of kind of factors to come into play, right? And so optimization can help with that. Okay. Optimization is actually used a lot in finance as well. So it's used to kind of predict market conditions and kind of optimize pricing to kind of maximize profit under certain situations. Okay. It's very broad, and it's definitely a good skill to learn. Of course, I think it's a good skill to learn because I'm extremely biased, but I think it's good to learn. Okay. Okay. So the way these the next two lectures are going to go is that today I'm going to spend kind of giving everyone kind of a crash course in optimization. We're not going to go over any algorithms or anything, but we're going to talk more about kind of what an optimization problem actually looks like, how it's different from kind of a traditional algebraic problem, and how we actually go about solving it. Okay. And how we're going to solve it is we're actually going to make use of MATLAB code. Okay. And that's traditionally how a lot of optimization problems are solved. Okay, so what we're going to talk about is how to set it up, what are the kind of important aspects of an optimization problem, and then how do we actually write the code to solve it. Okay. I say code, but it's nothing. Don't be intimidated by it. It's very simple. We're using kind of a built-in function in MATLAB. We just kind of have to feed it the right things in order for it to give us the right solution. Okay. Okay. So let's start with that. So let's start with optimization concepts and terminology. All right. And so if I had to sum up how optimization works relative to like an algebraic problem, I would say that it's almost kind of like a guess and check procedure. Okay. Okay. I call it guess and check because visually that's kind of what it looks like it's doing. It looks like it's kind of just throwing out kind of guesses and checking to see if it's good, right? In reality, it's a lot more complicated than that, and it's not just guessing randomly. Well, some algorithms do, but for the most part, it's picking kind of more educated guesses. But what it looks like is that it's kind of guessing and checking multiple times. Okay, these types of algorithms or these types of approaches are called iterative approaches. Okay. And so the answer that you get from an optimization problem is not going to be solved for in just kind of one go around. In fact, you kind of have to do it kind of multiple times, right? And so visually, it looks something like this. Okay. And I'll explain this diagram in a second. Let me just kind of draw it first. Okay. So we have kind of a cyclic kind of approach here. Okay. Okay. So the starting point is here. Okay. And what I'm showing you there is a vector called x vector, right? And so this x vector here, let me go ahead and I'll define terms down here. Okay. Below the diagram. Right. This x vector here is what we call our collection of design variables. Okay. I call them a collection because usually there's more than one design variable in an optimization problem. Okay. In other words, this x vector here represents, it's a vector of our unknowns, or vectors of the things that we want to solve for. Okay. Okay. And for our purposes, specifically for biomechanics, the unknowns in our system are going to be the muscle force magnitudes. Right. So those are the things that we want to obtain. And for any given optimization problem, we may have 3 or 4 or 5 different muscle forces that we want to solve. Okay. Okay. So the reason I say that we have to start there is we have to start with an initial guess, right? Remember, an optimization algorithm is traditionally kind of a guess and check procedure. And so in order to do that, you have to have your initial guess. So sometimes, it doesn't matter all too much what your initial guess is. Eventually, you'll improve it enough to get the final solution. But for some other cases, it does kind of matter what your initial guess is. So you want to be a little bit careful how you choose that. Okay. Okay. So the next aspect of the algorithms here is f of x. Okay. So f of x in this case is our objective. It's called our objective function. Okay. Sometimes it's called our model as well. Okay. You'll hear me use the term objective function more often, just because that's kind of how I learned this stuff. So, but sometimes other people call it the model as well. Okay. Okay. So the purpose of the objective function is to basically allow us a way to kind of evaluate how good our current guess is. Okay. So the objective function usually takes the form of some mathematical function, right? It's just like I kind of described there. Because as we kind of go through our optimization algorithm, right, we're gonna propose, or we're gonna try to guess lots of different combinations of muscle forces, right? And so we need to find a way, or we need to kind of devise a way to determine which guesses are better than the others. Okay. Okay. So this is really important, and you can't have an optimization algorithm without an objective function. Just because otherwise, then you just have an unsolvable system, right? And if you have an unsolvable system, then literally there are infinite answers that can that you can use for it. And so you need to have some way to kind of rank solutions, okay? And that's what the objective function is. Okay. And so the objective function, another purpose of it that we'll see is that this kind of gives us the criteria of how we can actually improve our guess. And that's kind of the cyclic nature of this algorithm here, right? And so this diagram is fairly simple, but it encapsulates kind of how optimization kind of works in general, right? And so you start at the top left. You start with an initial guess for your solutions, and in our case, these are the muscle forces. You run that through your system. You evaluate your objective function, okay? And then based on that objective function, then you then go and decide, okay, now that I have this objective function value, how can I actually improve this, right? And so from there, you're going to make small adjustments to your muscle forces. and then just kind of keep repeating this, okay? And if you repeat this enough times, sometimes it could take, sometimes it could converge very quickly. So maybe you only have to repeat this 4 or 5 times. But some harder problems, maybe you have to repeat this, 100 times, thousands of times, millions of times, billions of times. That's not uncommon, okay? But you do this enough, and then eventually what you're going to do is you're going to converge on the solution, okay? All right, so those are the basic characteristics of an optimization problem. So, if there's a couple of vocabulary that I want you to take away from this is I want you to kind of know what design variables mean, and I want you to know what objective function means. Okay? Because we're going to use those terms quite a bit in the discussion to follow. Okay, any questions on this? Okay. All right, so that was a very mathy explanation for how optimization works, and all of that is good, right? But when you're kind of learning something for the first time, the straight math definition usually isn't the most helpful because it's just a lot of jargon, it's a lot of kind of abstract thinking. But I think optimization is really nice because it has a very intuitive kind of feel for how it works. And in fact, I would make the argument that you probably make use of optimization every day in your own life without kind of really realizing it. Okay, so let me give you kind of a real life example. Okay, and then we'll relate it to kind of the concepts and terminology that we use in optimization. Okay. So for this example here, we'll do a little bit of a thought experiment. Let's say that you are just introduced for the very first time to the concept of pizza. Okay. And what you want to find, or what the optimization problem is that you want to find the optimal combination of pizza ingredients that satisfy your taste. Okay. I should maybe be a bit more specific. Maybe we'll just do toppings. Okay, sorry. All right. We'll assume that the sauce and cheese are going to be there all the time. They're going to be the same. Okay, so we're just looking at pizza toppings. Okay. All right. So pizza toppings is I feel like everyone has a strong opinion on, right? Some more correct than others, right? You like pineapple on pizza, then I don't know what's wrong with you, but it's a good example because there's literally probably millions of different pizza toppings and even more millions different combinations of different pizza toppings. Okay, and so this could actually fit into an optimization framework quite well. As long as you have the stomach for eating thousands of pizzas. Okay, so let's match this problem up with our optimization terminology. And then let's talk a little bit about how we can solve this using an optimization framework. Okay. Okay. So the first one is the design variables. Okay. Okay. So remember, the design variables are the unknowns in the system, or that's kind of what we want to solve for at the end. Okay. And in this case, that is our design variables are the pizza toppings, right? Which ones we should use on our pizza. Okay. We can even limit it even further. And so, we can say that, we'll say top 3 pizza toppings, right? And so your design variables will be in, topping 1, topping 2, and topping 3, right? So what you kind of choose for each of those. Okay. Next, we have the model/objective functions. Remember, the objective function is our mathematical way, or our way of kind of rating, which pizzas are more superior than the others. Okay. And so in this case, the only real way to know if you like a pizza ingredient or not is to make a pizza and eat it and see how you like it. Okay. Remember, we're imagining that we have no concept of pizza at all, right? So somehow, you woke up from hyperbolic training chamber, or from cryo sleep, or whatever, right? And so, you're learning about the concept of pizza for the very first time. Okay. And so now that we have these terms kind of established, let's talk a little bit about kind of how we'd actually go about solving this problem, finding the optimal combination of pizza toppings, right? Okay. And so we're going to start with an initial guess. Okay. And so in this case, it doesn't matter too much kind of what your initial pizza looks like. And so, let's say that we pick, I don't know, sausage, onions, and pepperonis. Okay. Okay. That may not be your optimal toppings. That may not be your favorite in the end, but we have to start somewhere, right? And so let's go ahead and make a pizza with these toppings. Okay, let's eat it and rate it. Okay. So let's say we'll imagine that you have a little score sheet of pizza. Okay, pizza score sheet. Okay. So this step right here would be basically evaluating your objective function. Okay. Okay, so we made our initial pizza. We ate it, and let's say we rated it. Let's say we didn't like it, right? So let's say that we rated it 3 out of 10. Okay. Now we come to the iterative part of the optimization algorithm. So now we want to improve our guess, right? And so we had our initial guess: sausage, onions, pepperoni. We didn't really like it, right? We want to do a new pizza, right? And so for our next pizza, because we didn't really like it that much, let's for our next pizza, let's try to avoid ingredients, or avoid toppings that are similar to sausage, onions, and pepperoni. Okay. So for our next pizza, let's say that we use ingredients, maybe artichoke, figs, and I'm trying to think what other disgusting things my wife might put on pizza. I like anchovies. She hates anchovies. We'll put pineapple. I hate pineapple on pizza. Actually, my wife would love that. I should try making it. She's when she's mad at it. Okay. Okay, and so for this step, you know, what we can see is that we're working to improve our guess, right? Okay. And then from here, we just kind of repeat the process, right? And so, you know, we're going to, you know, now that we have our next guess, this is our next combination of 3 pizza toppings. We're going to make a pizza with these toppings, eat it begrudgingly, rate it, and then we're going to see kind of how we can improve from there, right? And so you can just kind of keep doing this over and over and over again with different ingredients, maybe different combinations of ingredients, right? And then eventually, you're gonna land at the optimal pizza. Okay. So this process that I've outlined here, this is kind of a very natural thing, right? And so if you had a friend that somehow had no concept of pizza, you know, this is probably quite similar to the process that you would do to help them kind of decide what their optimal pizza ingredients would be. Okay. Probably realistically, if this was your friend, there'd probably be some bullying involved too, like getting him to agree with your own pizza toppings. But you know, that's a topic for another day. Okay, but hopefully, you know, this example kind of illustrates to you kind of how an optimization process works, and that's kind of what we're going to do with the muscle forces as well. Okay. All right. Any questions on this? Okay. There's one more concept that we have to go over here, and that's the concept of constraints. Okay. Okay. And so constraints are kind of you can kind of think of them as, or at least mathematically, what they are. They're additional equations that you can add to an optimization problem to ensure certain conditions are met. Okay. So constraints is something that will make use of quite a bit, because if you don't add constraints to your optimization, then it can really just kind of just be the wild west and just kind of do whatever it wants. Okay. And so some examples, and so I'll give you kind of I'll relate it back to the pizza example, but then I'll talk about kind of some examples that we're going to use in reality for engineering and for muscle force optimization as well. Okay. So some examples of constraints might be like a food allergy. Okay. Okay. And so if you're allergic to certain types of foods, certain types of toppings, that's going to limit which toppings that you can put on your pizza, right? Because generally speaking, when you eat a pizza, you don't want it to kill you, right? And so that's you want to make sure you avoid those types of you know those types of foods. Okay, right. Another type of constraint might be something like a budget, for kind of a more realistic engineering example. Okay. So any large engineering project has a budget that it can't exceed. Okay. Because if you were able to spend infinite money on a project, there would be a lot more solutions. But the difficulty of a lot of engineering is finding a solution that's within budget, right? And so that's going to place a lot of constraints in terms of what materials you can buy, how many people you can hire, things like that. Okay. So kind of more basic ones that we're going to see here. For our purposes in biomechanics is we need to place constraints on the amount of force each muscle can produce. Okay. And by that same token, we can place a constraint to make sure that the muscle forces are tensile. Okay. Basically ensuring that our optimization doesn't predict a compressive muscle force, because that's kind of physically impossible to do. Okay. And we can also place constraints in our case on the overall force that needs to be produced given a certain load. Okay. 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 And so we're going to add those constraints. And so, just to kind of be aware kind of what they are and kind of what they represent. Okay. And so before we kind of get into more specifics of biomechanics optimization, let's talk about kind of the steps that you need to do in order to set up an optimization problem. Okay. So this is probably going to be the biggest difference in terms of kind of what you kind of traditionally know as solving a problem, right? Because when you're solving an optimization problem, you're not actually solving it yourself. You're going to let the computer kind of handle the whole guess and check algorithm procedure. Okay, so you're going to be very hands off. But what you need to do instead is you need to kind of be very clear and very good about defining the problem. Okay. Okay. So you need to be very clear about what the design variables are, what they represent, what your objective function is, what its mathematical form is, what the constraints are, and all that stuff. Okay. Okay. So I have kind of a 3-step procedure here that we'll see it applied in the next example. Okay. And so step 1 is to define what the design variables are. Okay. Right. So you want to define what the design variables are, as well as their bounds and constraints. Okay. Okay. Step 2 is to define what's called the forward model, or I should say, we're going to define the objective function. Okay. So remember, the objective function is kind of our way to decide kind of which combinations of design variables are going to be good. Okay. This is where you can provide different criteria for different situations. Okay. And so if your objective was kind of energy conservation, that's going to define your objective function in a certain way. If your objective is performance, that's going to change your objective function. Or maybe your objective, or maybe your criteria is stability and performance, right? And so, a lot of the thought that you're going to put into an optimization problem is going to be in step 2, which is, how do we formulate our objective function and what does it represent? Okay. Okay. And step 3 here, we're going to choose an algorithm to solve our problem. Okay. And so the thing with optimization problems is that there are lots of different algorithms to actually solve the problem, right? So the kind of the framework that we talked about in terms of the pizza example, that's kind of the general kind of framework for an optimization. But the exact details of how it determines the guesses, how it improves the guesses, how it actually kind of goes back and kind of repeats and everything like that. The details for that are different in lots of different algorithms. Okay. And I think what's confusing and kind of, I think, overwhelming for people when they first start doing optimization is that there are probably literally hundreds of different algorithms that you can use. Okay. And out of those 100 algorithms that you can use, probably about 80% of them will work for your given problem. Okay. And so, you might be kind of, overwhelmed in terms of, what algorithm we choose, how do we find the ones that work, and so on and so forth. Okay. The good news for this is that, because optimization is so broad and it has kind of applications in so many different areas of like kind of economics, engineering, biomechanics, everything like that, right? If you're kind of sticking to just one problem area, and so for us, we're sticking to kind of one, I would say, kind of very specific application of optimization, which is muscle force optimization. Most of the time, if using the same algorithm will work for a lot of these problems, with some exceptions, of course. And so we'll talk about kind of what algorithms are kind of good for these types of problems and how we actually set that up in MATLAB. Okay, but technically speaking, you do have to choose an algorithm, and that's going to be an important part of your solution. Okay. Okay. So that's kind of the 3-step process. And so, what I have next here is an example. It's a very long example, so we won't be able to finish it today. But we'll start it today. And then, of course, I'm going to expect you to have photographic memory after Thanksgiving to kind of pick up this example again afterwards. No, I'm kidding. We'll kind of go over it again after Thanksgiving as well, just because that's 2 weeks in between lectures. But I did want to start today just to kind of strike while the iron's hot in terms of kind of discussing kind of a lot of things that we talked about today. Okay. All right. Any questions on that? Okay, so for the last 15 minutes today, let's start this example for muscle force optimization. Okay, and so remember, our goal, ultimately our goal with this section here is to basically take a motion, okay, that we've already done the kinematics for, that we've already done the inverse dynamics for, right? We're going to take a motion and compute all the individual muscle forces that go into producing that motion. Okay. Okay. Okay, so for this example, we're going to focus on the lower extremity. Okay. And so we're going to assume that we've already done our inverse, our human motion kinematics and our inverse dynamics analysis. Okay. And for our for our purpose here, we're gonna be analyzing the ankle joint during the walking gait. Okay. And so during the walking gait, let's say that we're going to be analyzing the part kind of near the end of the stance phase where the foot is kind of pushing off the ground. Okay. And so we have a net plantar flexion moment at the ankle joint. Okay. Okay. And that net moment is going to be 100 Newton meters. Okay. Okay. And so when we look at all the muscles that act at the ankle joint, we have 5 muscles that are acting there. Okay. 3 of these muscles can produce a plantar flexion moment, and 2 can produce a dorsiflexion moment. Okay. Okay. So our 3 plantar flexion muscles here. Our first one is called the gastrocnemius. Okay. So that's one of the big muscles that are in your calf. Okay. Second one is the tibialis posterior. Okay. And 3 is the soleus. Okay. All 3 of these are different muscle groups that kind of make up your calf muscle. Okay. Okay. And our 2 dorsiflexor muscles here, these are going to be the muscles on the front of your leg. We have 2, and so the first one's called the exterior digitorum longus. Okay. And the second one is the tibialis anterior, which is the antagonist muscle of the tibialis posterior. Okay. So those are our 5 muscles, and we want to basically use optimization to determine how much each muscle is going to act. Okay. So since this is our first optimization problem here, we're keeping things fairly simple. Okay. And in fact, you can tell from the problem there that we're only looking at our net moment. Okay. Because normally in inverse dynamics, if we remember from last week, not only do we get net moments at each joint, but we also get net forces as well. Okay. But we're not considering that in this case. Okay. So just to kind of keep things simple, we're only considering the net moment. Okay. And so with that assumption there, we can actually eliminate two of these unknowns already. Okay. And so since we want a plantar flexion moment, right, the only possibility or the only way we can produce a plantar flexion moment is with the plantar flexion muscles, right? And so in this case, because we're not considering the joint forces, we can kind of eliminate the 2 dorsiflexor muscles. Okay. Okay. But in reality, even when you're producing a plantar flexion moment, right, in order to balance all the forces, the raw forces at the joints, your antagonist muscles have to act as well. Okay. But we're not considering that in this case. So we're going to basically kind of cut down our unknowns from 5 to 3. Okay. Okay. And so with that out of the way, we can go ahead and define the balance for each of these muscles. Okay. Okay. And the way I'm going to do this is I'm going to specify the maximum amount of force that each muscle can produce. Okay. And this is going to be a function of its cross-sectional area, kind of as we kind of mentioned a few times in the class. Okay. Okay, so for the gastrocnemius, the maximum amount of force that it can produce is 4,097 newtons. Okay. For the tibialis posterior, we're going to assume that this maximum force is 3,052 newtons. Okay. And then for the soleus muscle, let's say that this maximum force is 6,435 newtons. Okay. So that's going to be the upper bound for each muscle force in terms of how much they can produce. Okay. All right. The other piece of information that we need, because we are given a moment here, we have to determine what the moment arms for each of these muscles are. Okay. And so that's going to be given to us in the problem. So the moment arm for the gastrocnemius is 3.9 centimeters. Okay. For the tibialis posterior, we have 0.8 centimeters. Okay. And then for the soleus, we have 3.6 centimeters. Okay. A jolly old time out there. Okay, so the last thing I want to do today, we're not going to get to the objective function today, and I kind of want to give that kind of a more thorough discussion anyway. Let's end today by talking about the constraints for our variables. Okay. So we have 3 design variables in this case, right? We have our 3 muscles, our gastrocnemius, our tibialis posterior, and our soleus, right? So the first thing we're going to define here are the upper and lower bounds for each of these variables, okay? Okay, so for the gastrocnemius, okay, we know its upper bound is 4,097, but we have to set its lower bound as well. And so our lower bound in this case is going to be 0, right? And so the lower bound amount of force a muscle can produce is none, right? Which seems obvious, right? But we have to make sure that our muscle force doesn't go negative as well. Okay? Remember that requirement that we had before, that our muscles can only produce tensile forces, right? And a tensile force is defined as a positive force. Okay? Okay. And at this time, we'll go ahead and define our symbols for each muscle force, right? So for the gastrocnemius, we'll call it Fg. Okay. For the tibialis posterior, again, its lower bound is going to be 0 newtons. Okay. We'll call it Ft, and its upper bound is 3,052. Okay. All right, and then for the soleus force, we have 0 newtons. We'll call this Fs, and its upper bound is 6,435 newtons. Okay. Okay. So that's the baseline, right? And so we need to, at the very least, we need to make sure that the muscle forces that we compute from our optimization respect these constraints, right? So first of all, we don't have a negative muscle force, and we don't produce muscle forces that are above their maximum. Okay. Okay. We have another constraint, and this is a constraint based on the amount of force, or the amount of the total amount of moment that we need. Okay. Because that's given to us directly in the problem that the net plantar flexion moment that we need is 100 Newton meters. Okay. And so we need to make sure that all three of these muscles in combination are producing that net moment. Okay. All right, and so to do this, we're going to use our typical moment equation. So we're going to take our force multiplied by its moment arm. Okay. And so the moment arms were given to us in the problem there. Okay. And so for the gastrocnemius, its moment arm was 3.9 centimeters. And so we're into 0.039 Fg. Okay. Plus, make that G look a little bit nicer. Okay. The moment arm for the tibialis posterior is 0.8 centimeters. Okay. And so that transformed into meters is 0.008. And then we have Ft. Okay. The moment arm for the soleus muscle is 3.6 centimeters. And so we have 0.036 Fs. Okay. So all three of these combined have to equal 100 Newton meters. Okay. So no matter what combination of forces that we find, we have to produce 100 Newton meters of moment. Okay, because that was given to us from the inverse dynamics analysis. Okay, so that's one more constraint that we're going to use in this problem. Okay, any final questions on this before we wrap it up for today? Okay, and so when we come back in 2 weeks, we'll come back to this example, and we'll talk about the objective function that we can use for this problem. Okay. Okay, so thank you guys for coming today. Remember Wednesday is our midterm exam, so please make sure you're here for that. Oh, one more thing. This evening, I've already heard from I think the majority of groups. So I think most people have a group in the class already for the final project. So that's great. If you're not in a group, you'll probably be getting an email from me tonight, and I'm just going to place you together with other people. Okay. And so if you have a group and you haven't reached out to me, you have until maybe about 8 p.m. That's probably when I'm going to go home today to let me know. If you don't let me know by 8 p.m., I'm just going to put you in a group. Okay. All right. So thank you guys for coming today. I'll see you guys in class on Wednesday for the exam. Yes, yeah, so Maxwell, I did reach out to the other team. I think I CC'd you on an email with them, but I'll double check that tonight. Yeah, I was able to find a team for you. Yeah.
Just want to double check with you because I joined a team kind of last minute, not really. I'm in Sebastian's team.
Yeah.
Just wasn't sure if I was included in like the.
He was, yeah.
Oh, okay,
Sebastian, let me know.
Okay, perfect. Thank
Yeah.
you.
Let's talk a bit more offline, Maxwell, about that situation. Okay. Yeah, send me another email, or I'll email you when I get back to my office. Yeah. Yeah. What's up?
I'm in your 450 forecast.
Yeah.
And I've been trying to upload the thing, but says like submission failed. Because too many files.
Shouldn't be. You should be able to add as many files as you want. Start with just so you can update your assignment afterwards. So let me just upload just the first one, and then
I can do it by parts.
You can do it by parts. Yeah. That's fine.
Okay.
Yeah.
Okay. Thank you.
Yeah.
Went to your office, right?